This is the Building Automation Monthly Podcast with Phil Zito, episode 110. Hey folks, Phil Zito here, and welcome to episode 110 of the Building Automation Monthly Podcast. And in this episode, we are going to be continuing from the previous episode 109, and we're going to be discussing control sequences. So if you haven't went and listened to episode 109, I really encourage you to do that. I'll do a brief recap here, but it will not do justice to the 30 minutes that was episode 109. So essentially what we went over in episode 109 is that a control sequence is the way of controlling a piece of HVAC equipment with a building automation controller. So a building automation controller has inputs and outputs, and it processes these inputs and does something to the outputs based on the control sequence. And when we look at control sequences, we're looking to focus in on four different things. The first is the enable modes, what turns on and off the control sequence. The second is the control mode, what actually causes the different variables and outputs that are being controlled by this controller to do whatever they're doing. And I use those terms specifically, variables and outputs, because we need to remember that we are not always just controlling outputs. Sometimes we're controlling variables. Sometimes we are going and averaging a series of values and sending it to another controller for it to control an output. And so that's why it's really important for us to make sure we pay attention to that as well. Then we have the alarms, and I always say that you should focus on the alarms after the control modes and after the enable modes, because the alarms should always override everything else. And what I mean by alarms is if you have a high pressure shutdown, low temperature alarm, smoke alarm, those alarms, those life safety or equipment safety alarms should take priority over all the other control modes and enable modes that we're going and looking at in our sequence and programming in our programming. And then finally, you have auxiliary modes. And auxiliary modes are quite simply anything that is run off of this controller, but is not necessarily tied to the sequence. So maybe you run a toilet exhaust or an exhaust fan when the air handler's on. It's not necessarily critical to the sequence, but it's tied to the sequence or tied to the controller. So that's the kind of four parts. Now what we're going to do here is we're going to dive into a VAV reheat sequence of operations. We're going to dive through that, we're going to pick it apart, and I'm going to include a PDF of that sequence at the show notes page, which I'll give you at the end of the episode. I'm also going to include a video that is going to go through kind of space control fundamentals. We're going to talk a little bit about that in this podcast episode, but I'm going to include a much more in-depth video also in the show notes. So you'll get that page address at the end of the video. Okay, so VAV reheat sequences. What exactly is unique about VAV reheat? And what is a VAV if you've never heard of the term VAV? So VAV stands for variable air volume. It's basically the opposite of a CAV, which is constant air volume. So essentially, you have two ways of controlling air volume in the space. And that's our primary goal with these units, is controlling air volume, because air volume controls temperature in most cases. As we'll see with a VAV reheat unit, that's not exactly true because we have a reheat valve, but it's mostly true. And that's what we're looking to focus in on. So like I said, a VAV is a variable air volume unit. And what happens is, within a space, think of a cup, okay? So if you're driving, don't look for a cup. If you're not driving, just look for a cup or some sort of container. If you were to fill that with water, eventually it would overflow, right? It would fill up and overflow. And what you would have to do then is you would have to let some of that water out. Well, that's the exact same thing with a space. We don't often realize that air has volume. It has mass. It actually has weight. because of the molecules that are in it. Granted, it's very light compared to water and liquids and solids, but it has mass nonetheless. So when we talk about air volume, we have this volume of air that we're pumping into a space. As I look up here, sitting at my desk recording this podcast, I see a space diffuser sitting here in the corner by the window. And that's very common to have a diffuser by the perimeter because it creates an air curtain of sorts. And the reason I have that is because I have a constant volume multi-zone unit, which is going to be heating and cooling air and providing it throughout my house. In a VAV unit scenario, you'll often still put the diffuser, put the air supply near kind of the exterior of the building to either heat or cool, because you have heat gain and heat loss if you're on an exterior part of the building. Another thing with this is the return. Quite often in VAV units, you have what is called a mixed air unit as your air handler. And what that means is you're mixing return and outdoor air, because you have to have a certain amount of outdoor air. If you've ever been in a space and you started to get really tired, it's most likely that you didn't have proper outdoor air supply or proper air changes, a concept we'll cover in just a second. But outdoor air, it counteracts the effect of CO2 buildup, which is what we exhale as humans when we breathe. We breathe in oxygen, we exhale CO2, and that's kind of the respiratory process. And what happens is that CO2, when you breathe it, it makes you tired because you're not getting enough air coming into your lungs. I don't profess to know the physiological aspects of this, but I would imagine it has something to do with not getting air in the right concentration or oxygen in the right concentration. But whatever it is, it causes you to become quite tired. And so what we often will do is we'll have minimum outdoor air ventilation, and that will come in. And that's delivered into the space through the supply and then exhausted or returned to the unit through the return damper. So the unit will draw air back. Now, when a full air volume is added to a space and removed, that's called an air change. That's when the full volume of air is changed. Now, typically in common office rooms, you've got about 4 air changes an hour. So that's why if you change the temperature on an office space, for it to kind of settle in takes a couple minutes, because you're looking at having to go and mix all this new air volume in there to either cool down or heat up the air. That's why VAV units are what are called slow acting loops. Whereas when you change fan speed, pressure will tend to change. The air pressure will tend to change rapidly in a space unless the space is oversized, which it's hit or miss whether spaces are oversized. Some engineers oversize, some undersize. But if a space is oversized, then you might hit set point very fast, but typically it'll take a little bit, and that's what's called a slow acting loop. A loop being, hey, I've got a space temperature set point, and I'm going to adjust airflow based on the difference between space temperature and space temperature set point, compare the two, and then keep adjusting airflow. And that's a process loop that I'm looping my finger here. You can't see me spinning my finger in a circle, but that's a loop. All right. So as I said, air has volume, and it also has temperature and moisture properties. So when you're adding air, oftentimes we will go cool air to 55 degrees, and that means the air becomes fully saturated at the air handler, and then we'll subcool it to remove moisture, because what happens is air hits this thing called dew point, right? And when you hit dew point, what happens is that no more moisture can be in the air. It's all condensing, and it causes condensate, that's the moisture, to form into water droplets that drip down into a condensate pan and exit the airstream. Then when the air naturally gets reheated as it mixes with the air in the space, the temperature rises, which causes the humidity, the relative humidity, to be lower because the amount of moisture that's in that air is now lower. So that's why we aim for 55-degree air as our set point, because downstream from discharge means we're typically 52 at the coil, give or take, so we're actually going and draining that moisture out. I know this is about control sequences, and some of you all are like, I already know all this. Some of you don't know this, and it's really important. This is kind of what I hammer a lot in my courses, is understanding the why behind the system. As anyone can read, I could literally in probably 5 minutes read you the VAV box sequence, explain it to you, but without this kind of background knowledge of why these things are happening, you're going to go and with some basic programming knowledge, you'd go write your program, but as soon as something messes up, or as soon as a design set point, design max or min CFM isn't quite right, you won't be able to understand the indicators of why things aren't working. Okay, so back to what I was saying. It has moisture and it has temperature. Now your goal is to either heat or cool the space. And you do that, like I said, by mixing a volume of air. And occasionally you can reheat that air, which is something that we'll go through as we go through this sequence. And I also mentioned CO2 and minimum ventilation, but here's something that a lot of folks miss up. And I see this a lot in retrofits. I also see this a lot in tenant finish outs where people are being really cheap and they don't want to pay for a balancer. What they do is oftentimes folks will think that minimum airflow means the amount of outdoor air that you need for that space. So let me give you an example. If you needed 5 CFM of outdoor air per person and you had 10 people in a space, and so you said, okay, then I need to have 50 CFM of outdoor air. Well, what some folks will do is they'll say, oh, okay, well then my minimum set point for my VAV box, well, that should be 50 CFM. But here's the problem with that. Unless you have a 100% outdoor air unit, you're not getting 50 CFM of outdoor air. Most times, what you're getting at the, what's the word I'm looking for here? Mixed air unit. When you're at the mixed air unit, you're 10 to 20% outdoor air damper. So 10 to 20% of that air volume that's being supplied to your space is actually outdoor air. The rest is mixed with return air from the space. So you're not getting a true 50 CFM. And that's I see this a lot in schools. I see this a lot in office buildings where I would do service calls and folks would say, man, we're getting tired. And someone would be like, oh, change the lighting. It's because the lighting you're tired. And in some cases, yeah. I mean, I use bright white lights because it's proven, at least quote unquote, scientifically, that's what I've heard, and every lighting manufacturer will tell you that warm light calms you down and cool bright white light, 5,000 Kelvin, wakes you up, keeps you energized. Well, the thing is that that's all well and good, but if you're not providing the right amount of outdoor air, which is very common, because folks will go and they'll make a tweak or the mechanic will change something, and then all of a sudden they're like, oh crap, we forgot what the minimum outdoor air is. Oh, we'll just set it to whatever the CO2. Let's go look at ASHRAE 62.1 and figure out for the space what outdoor airflow we need per person, and then we'll calculate that. Oh, we need 50? Oh, okay. Well, we're going to set the minimum to 50, but it's not 50. You see, I know this is a long little diatribe here, and I know you're expecting control sequences, and I promise you we will get to that. But do you see the problem with this logic? Do you see why you have to understand kind of the bigger effect on the system? Because if you simply said, oh, 50 CFM, and then you had the outdoor air at 10-20% of damper for the mixed air unit, that would not be true 50 CFM of outdoor air. So I know that's a little rabbit hole there, but it's a really important rabbit hole because a lot of you who are doing service, I really challenge you next time you go to a school or an office building, ask them how the air feels. Does the air feel muggy? I mean, if you've been in the trade long enough, you can walk into a space and you can feel when air is stagnant. You can taste it almost, that the air just tastes old. I don't know how to describe it. It just it smells old. It's like visiting my grandparents, right? I mean, it's old. And so that's the thing. That's what you've got to go and pay attention for. All right. Now, as I was saying, we are going to get to the actual sequence of operations. So let me open this up real quick. All right. So taking a look at the sequence of operations, which I will attach to the show notes so you'll be able to see that. This sequence, I've conveniently organized it in such a way that our enable modes are right at the front for the unit. And this is pretty common for a VAV unit, is to have an occupied mode and an unoccupied mode. So occupied mode, you will tend to have a temperature. So in this sequence, we've got an occupied mode and it's saying, hey, when it gets above 75 degrees, we need to cool the space. And when it gets below 70, we need to heat the space. This is very common. What that means is you will tend to have two different ways of controlling the VAV box. You'll tend to have cooling CFM set points, because the way you cool with a VAV box is that you go and you increase to quote unquote max cooling CFM, and you increase that, and what happens is as more CFM comes in, then in theory that air is 55 degrees, it mixes with the space and removes the heat from the space, absorbs the heat, and then is returned to the unit where it's recooled. Now you will get into design days where that won't happen. What will happen is, maybe you get above what the unit was designed for, the air handler or the VAV. Maybe it was designed or sized, especially up here in the north, sized for 90 degrees outdoor air, and you get a 105 degree day, and then every space is hot because the chiller can't keep up with the load. Thus, the cooling coil can't keep up with the load, and thus the VAV box doesn't have enough cooling to cool. Now, on the flip side, you have heating, right? And heating here's how VAV units work before I go through that. And VAV units will tend to be cooling only units on the interior of the building, unless you have a specific reason for heating. For example, maybe you have some equipment that can't get too cold or whatever. Or maybe you have a space that is very temperature sensitive. Maybe it's an operating room or something like that. In that case, you would have a heating valve usually as well, so that way you could control. But in most cases, the interior spaces are cooling only, meaning all you have is the damper that you can open or shut, and that's a key point with VAV boxes. You heard me say shut? You shouldn't shut VAV boxes. What you should do is you should reduce them to their minimum airflow, okay? Because what happens is you'll hear a lot of folks who say, when my air handler starts up, it trips on static safety. Well, a lot of programs these days will actually go and take their VAV boxes and they'll program them to be tied to the air handler. So when the air handler is enabled, the VAV box comes on. Here's the problem with that. These programs will often close the VAV dampers, because what these programmers or the sequence writers or whoever's coming up with this isn't realizing is that when you close those dampers, they have a 90-second stroke time. Your VFD does not have a 90-second stroke time. That sucker can go from 0 to 100 pretty fast, 10, 20 seconds. And then you've got full supply air. And the problem with that is now you've got this fan that's running all out. You've got these dampers that are still opening. The static pressure starts to build up, and boom, that static pressure, high pressure alarm trips, and now the unit is stuck there. And so what I recommend is having a minimum set point. Now, what's going to happen when the air handler is off, what that means is that those cooling only boxes and reheat boxes are going to open to 100% to maintain that CFM, because the air handler is not supplying air. Now, one last thing before we continue this sequence, that has an adverse effect. A lot of folks like to write their sequences to turn on air handlers when, 2 or 3 more or more dampers are 100% or 50% or greater. So you can't use that kind of logic when you're allowing your units to go and open up and close down, or open up their dampers when they're not getting air. And then you also have to be cognizant of PID windup. Man, we're going down so many rat holes today. But it's just, can you see why it's not as simple as just saying, all right, you control the temperature, you control the CFM, you open the damper, you open the valve, you're done. There's so many intricacies, and that's what I find so exciting about building automation, is there's so many just interrelated concepts. Oh, well, if I close my VAV dampers down and I don't have proper ramp time set on my supply fan VSD, well, then my VSD is going to trip. So I need to be careful there. But also, if I open up all my dampers and my unit is looking for those dampers to be open for its start enable, I may turn on my unit when it doesn't need to be on. And also, my PID loops, if I don't properly set those and tune those, they may get wound up because they're never going to get the CFM they need. And so maybe I need to disable. Here's a trick. And I promise we'll get right back to the sequence. I did not plan on having so many segues in my show notes here. But here's a really cool trick I like to do. I will often, when the unit is unoccupied and there is no airflow from the air handler supplying it, I will disable the PID loop and I will command the damper to 100%. I'll have a switch in there that will disable the PID loop and will go and send a 100% signal to the output for the damper, and it'll keep that damper 100%. And as soon as the air handler is enabled, then I will allow that damper to start controlling to airflow. And that way, I don't run into high pressure alarms. That has saved me so many times, and it's been really helpful, and it keeps the PID loops from winding up because you keep them disabled until there's actual airflow. All right, so as I said, there's occupied mode set points and unoccupied mode. And what happens with this sequence is when the zone temperature is greater than its cooling set point, okay? So oftentimes what will happen is you'll have a set point. So you'll have first space a set point of 72. And then you'll have this concept called deadband. And deadband is the amount of temperature in degrees between the cooling set point and the actual set point. Typically, this is 2 to 4 degrees. So what that means is if your set point is 72, your cooling set point would be 74, and your heating set point would be 70. And what happens is between 72 and 74, nothing happens. So this is kind of this is from the days of electromechanical controls where your wall thermostat at your house would go and it would wait until you got kind of a degree or 2 degrees above that set point to actually turn on the cooling. So this is proportional control. This is a proportional difference. So what will happen is that that cooling PID loop will not be enabled until you are 2 degrees above that zone temperature, okay? So that's what's going to happen right there. And then what happens from that, okay, so you're 2 degrees above that zone temperature set point, your cooling is enabled, and your damper starts to go from minimum airflow all the way to maximum airflow to control to zone temperature set point. And how it does that is you've got 2 PID loops, you've got a cooling PID loop, and that output goes to a reset that resets a CFM set point that goes to a second PID loop that controls damper output. And this is how you modulate between minimum required zone ventilation and the maximum cooling. And it's pretty much the same in unoccupied. Now, reheat is a little different. So what happens in a non-reheat box is when you fall into that heating set point, you will go to minimum airflow. Typically, you'll go to minimum airflow, minimum cooling airflow. However, when you have a reheat mechanism, whether that's electric reheat or hot water reheat or gas or steam. Yes, I've seen steam in VAV boxes. It's horribly difficult to control, Anyways, that's neither here nor there. So in this case, in this sequence, it's hot water. It's a reheat valve. So first thing, we need to make sure we have a proportional valve actuator, because controlling with floating or with incremental, whatever you want to call it, actuators, it's just a pain in the butt. Let's control with proportional, give ourselves greater accuracy, not have to worry about the stroke time and all that fun stuff. So what happens is you've got this reheat valve, and until you get to the cooling set point, so if our set point's 72 and our heating set point, until you get to the heating set point. So our set point's 72 for the space. Our heating set point is 70. Until you get to that point, nothing happens. You're at minimum airflow. Then once you get to that point, what happens is you go to this called heating CFM. So it's slightly higher than minimum airflow. It's typically about 20 to 30% of max airflow, somewhere in that. That's not a hard set rule, but that tends to be where it ends up. And so that's your heating CFM. The reason you do that is because you want to bring through enough air to fully absorb the heat transfer from the supply air to the discharge air. So what's happening is that coil is going to gradually open up as it continues to get colder. You have a PID loop for the heating valve. And as that opens up, that is going to go and drive your heating valve. And it's going to drive the heat, it's going to heat up the discharge air, and it's going to start to warm the space. If you do any more than 20-30%, you'll tend to give people a blast of hot air, especially with electric reheat, which can get really hot, and it'll be very uncomfortable. That's also why you'll tend to have a discharge air temperature sensor for your VAVs that have reheat. You're not controlling, this is a common misunderstanding, you're not controlling that VAV box's reheat off the discharge air temperature. You purely have that to make sure the discharge air temperature doesn't get too hot, because you don't want to be blasting 120, 140 degree air on the top of someone's head. That will make them extremely uncomfortable. You're tending to average anywhere between 80 to 95 degree discharge air, especially with hot water. That's kind of where you're at typically. And what will happen is that will heat up the space, that air will then mix, and you will start to warm up the space. And that's the VAV sequence. I mean, now do you see why I spent so much time on the air side stuff, on the air handler, going through that, why I spent so much time talking about outdoor air and humidity and minimum ventilation? Because all these things are interrelated. And so my greatest word of advice, I get emails every day, folks asking, hey, I'm going into building automation, what advice would you give me? Or I'm starting to do more programming, what advice would you give me? It would be to go beyond the sequence. I mean, how many of you, if we're honest here, have actually read ASHRAE 55 or read ASHRAE 62.1? I get it. That stuff is boring. I mean, it puts me to sleep. But the reality is, understanding that gives you power. It helps you to understand why you're making the choices you're making. And when you understand ASHRAE 55, you start to understand why diffuser placement is so important and diffuser style. Because one of the things, so ASHRAE 55 is how you determine your zone temperature set points, essentially. It's the standard for thermal comfort, and there's this thing called the thermal comfort corridor on a psychrometric chart that says, hey, within this temperature and relative humidity, people are comfortable. But it also talks about clothing. It also talks about physical activity level. It also talks about airflow. That's why if you ever go to a gym, I've been going to this CrossFit gym lately, and it's cold. I get in there, it's 30 degrees, 40 degrees. I can see my breath. And they turn on this floor-mounted electric heater that just blasts heat out. But by the time I'm done working out, just all the heat coming off of our bodies, it actually feels quite warm in there. And that is because of the metabolic effect on comfort. So if you don't take that into account, if you're sizing for a gym, or if you're sizing for a patient room where the people are immobilized and they're sitting in a bed and they can't do anything. I mean, there's this running joke. Folks are like, oh, old people are cold in hospital rooms. Well, maybe it also has to do with the fact that most people, I get cold in hospital rooms. I'm normally hot because you're immobilized. You're sitting there, and oftentimes, where's the diffuser? It's right over your head, and it's blasting cold air on you, so you feel cold. So you need to be aware of these standards and what they mean, because ASHRAE 55, moisture, temperature, clothing, the metabolic effect, how much people are working out, all these things come into effect when controlling temperature. And the same with ASHRAE 62.1, when you're controlling outdoor air, understanding space type, because a classroom is completely different than a cafeteria. And oftentimes I'll see folks go and do a minimum ventilation for a cafeteria or for an auditorium, which is horrible because you're bringing in this outdoor air and conditioning it when you could literally go pay $200, get a CO2 sensor, have that wired up for a couple $100 and programmed, and then shut your outdoor air damper when no one's in that space. I mean, if you have a cafeteria, if you have an auditorium, if you have any space that has periodic utilization and it's directly fed by a rooftop or 100% outdoor air unit, you need to be using CO2 control. That way you can completely shut that damper because you are conditioning air that you don't need to condition. All right. So this went a little bit longer than I thought it would, but we talked about a whole bunch of topics that are really, 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 really important. We actually started to unpack several of the airside topics, and in the next episode, we are going to dive through an air handler. We're going to go through an air handler, we're going to take a look at how air handlers are controlled, and we're going to read through the sequence and kind of talk through that as well. So everything I talked about is available at buildingautomationmonthly.com/110. Once again, that is buildingautomationmonthly.com/110. If you liked this episode, if you were like, man, this was really cool how Phil went through this. This is just a taste of my online course on control sequence fundamentals. And I really encourage you, if you feel that, man, I don't understand how to control equipment, I don't understand what equipment does, I don't understand what equipment is, then I'm telling you, that will hold you back from where you can go in your career. That was the biggest decision I made that I didn't know I was making at the time, was to go and learn control sequences and how they function and how they operate and control HVAC devices. And if you learn that, I mean, that gives you some power with your career. It gives you power in meetings. It gives you power with just the satisfaction of knowing that you could tackle service problems, install problems, design problems, because they're almost always related to the control sequence and how it was implemented. And so if that sounds like something that improving that would be a big benefit to your career, I really encourage you to check out my Control Sequence Fundamentals course, which I linked to in the show notes at buildingautomationmonthly.com/110. Thanks a ton again for being here. Give me some feedback in the comments at buildingautomationmonthly.com/110. Let me know how this is working for you, if you're able to kind of take in these deeper episodes. I know the past several episodes I've went much deeper into the concepts. I just feel that for those of you who have been following along since the beginning, it's kind of time for us to go there. And so let me know what you think. I really, really want to hear from you. Thanks so much for being here on another episode. I apologize for this being a day late. My daughter had her 12th birthday yesterday, so there wasn't going to be any podcast recording on her 12th birthday. But now that that's done, all the rest of the episodes should be coming out Monday at 6 a.m. like normal. This episode is just kind of a fluke with it coming out on a Tuesday. But thanks so much for being here, and really happy that you chose to listen to this again. Thanks so much, and I can't wait to talk to you again next week. Take care.